Hello friends, so in today's tutorial we are going to deal with how to implement callback while training deep learning neural network using TensorFlow. So this is the TensorFlow playlist or TensorFlow tutorial series, and this is the second tutorial of this series. So let's start, right? So first we have to import TensorFlow, and as you have seen in the previous videos tutorial as well, right? We are just importing TensorFlow, and while import we'll use this underscore version for printing the version of TensorFlow, right? Now today we are going to deal not going to deal with some random data. We are going to deal with this fashion MNIST data set, which is pretty much a basic tutorial data set available inside TensorFlow right now. So it's a 28 cross 28 pixels grayscale data, basically a image data for all kinds of clothing images, and it has 10 labels from t-shirt to ankle boot and categories along with that. So it's a pretty good starting point for anyone who is looking to expand their skills in your vision cloud vision side, or in part of particularly in deep learning, right? So for accessing this data we are going to use tf.keras.datasets API. Okay, so as you can see, this fmnist object contains the whole data set, and we are calling it from datasets module of keras, which we are getting it from TensorFlow, and we are calling it this fashion underscore mnist contains this, right? So let's just load this object, and if you print this mnist object, you will see it is nothing but a module that contains this data set. Okay, so it's kind of okay. Keras has already implemented this data sets via their API calls, so you can easily load and work along with this. So if you use the load data of this object, right? So fmnist now it is available in our worksheet, and if we are going to use this load data function, then it will give us two tuples. So you can see this is tuple number 1 and this is tuple number 2, and this every tuple contains a list. This one is a list and this one is another list. This one contains all the images and this one contains all the levels of the images. So let's just load this. So images are nothing but, as you have seen in the top, right? It's a 28 cross 28 matrix, right? Or array. So now for looking inside of the images, what we can do, we need some libraries, right? So NumPy we are just taking for numerical processing here, and Matplotlib for plotting out the images here. Okay, so let's we have just we want to share the image of, let's say, 0th index. So we're just idealizing this index to 0. Then what we are going to do is nothing but we're just printing the levels here. Okay, so you can see these training levels. So it's a list. So for accessing list you need indexing. So this is the index we are passing, and the same thing we are doing for with the images. So it's nothing but a 28 cross 28 matrix, right? So if you do a plot dot show, then you can see the images. Okay, so what you have to remember in this, let it print first. Okay, now why it is taking too much time. So as you can see, the run is completed now, and we have the image pixel array. So this is your 28 cross 28 matrix. Okay, as you can see, it is forming a ankle boot kind of a structure, right? And the same thing with plot.imshow. with that method we are fetching that image. So things you need to remember for showing any image, you can use this plot, that means matplotlib.imshow. This is one thing that you have to remember, and you have to remember this. If you are going to use MNIST from TensorFlow or Keras API, it provides you two set of tuples here, one training and one test, and each tuple contains two set of list which contains your images and labels. Okay, now moving forward. Now, if you just change the index, you can see different kind of examples. So right now, I'm having also example with indexing of 42. So you can see this is a different image of ankle boot. Then same code, copy and paste, and I'm having a different set of index, index 23 here. Now, if I do that, I'll get a different set of thing, right? Okay, so I don't know what it is. Let's see the level. It says that 8 number level. Okay, so in 8 we have backs. So okay, that is the third example, is nothing but a backs example. So till now what you have learned is that how to load data, MNIST data set using TensorFlow or Keras API particularly. Second one, what is the function of this load data method, and third one, how to visualize the images using matplotlib. Okay, now moving forward, first thing that you have to do for any vision is to normalize your training and test data. Okay, for smoothing of your training work actually. So right now, if you see, you have 28 cross 28 pixel data, right? So basically each cell represents a pixel, and the range is from 0 to 255, right? So if you make this range from 0 to 1, then the algorithm can work much more faster, and that is what it's called normalization. Okay, or basically scaling kind of approach. So let's perform that. And once this is done, now what you can do, now you plot the same thing. Okay, now let's just plot the same thing, and let's see the array. Now you can see, right, same image you can see. So there is nothing change here, but here there is a difference, right? Now it is normalized basically from 0 to 1. Now model building, yesterday also in last tutorial we have seen. So what we will be using, we'll be using first of all sequential. So it defines the sequence of layers in neural network, that means stack of the neurons. First thing we are implementing here, as it's a vision problem, this flatten method. And why we require this flatten method, just as you know that our input is a 28 cross 28 pixels matrix, right? So to flatten things out and make it a single vector, basically one dimensional array, we require this method to make it a basically a flat structure, right, from the definition. Okay, you can also go and read about these things. So I'm just, everything is under your Keras API, so you can read more about all of this from here, right? So it comes under your reshaping the layers, right? So this flatten how it works. Okay, and then the next one is a single dense layer neuron layer, where we are implementing 128 number of nodes or neurons basically. And the third one is 10 nodes neuron layer. Okay, and this one is your output layer basically, this one is your input, and this one is your hidden layer. Okay, and one thing you are implementing here is the activation function. So tf.nn for neural network, and ReLU for ReLU activation function. The definition of ReLU activation function you can see. I hope already you people knows about all of this, right? So what ReLU does, or activation function does, or it's basically brings non-linearity to your neural network, right? So neural network is nothing but identifying functions that has some pattern, right? So for that pattern you require some non-linear functions, right? Otherwise it's nothing but a linear equation. if you see the neural network, how it works, right? So this ReLU, this is the definition of ReLU, right? So if let's say you are passing x and x is greater than 0, then it will return you the x, or else it will return you the 0. That means it will never give you a non-negative, non-positive function values, basically, not functions. Sorry for that. Now, so what you have learned here, so the basic building block from the very outer shell, it comes from the sequential. So you required one sequential to form the whole neural network. Then first of all, what you required for image data, you need to flatten this thing, you have to remember. Then whatever dense neural network or dense layer you are passing in form of your hidden layer. And the third one is your softmax, right? And this 10 is you have to make it match exactly with the number of levels that you are passing in your data. So we have 10 levels, right? So that's why we are passing 10. And the second one is the activation function. So in the output activation, we are passing softmax for output generation, and in hidden layer we are passing ReLU as an activation. Okay, so you can read much more about softmax here. I'm not going to consume a lot of time here. Just only one example I have set here, how softmax works. So as you can see, in inputs we have one numpy array, contains four one-dimensional, what you can say, scalar, basically it is. Okay, 1D array you can consume. Then we are converting it to tensor, as we are dealing with TensorFlow, right? So tf dot convert to tensor, and then you pass any array or any numpy array, basically it will convert the inputs to TensorFlow comfortable tensors. Then what we are doing, we are only just printing the input, and once that is done, same thing we are calling, right? tf dot keras dot layers dot dense, and in there we are passing this tf dot n and softmax, and here tf dot keras activation. From activations we are calling softmax, and within that activation we are passing this input tensor, and we are just printing this output as a numpy array. So this is particularly this whole code is doing. Okay, now this sum is nothing but what is the basic functionality of softmax is that if you sum all the elements of this array, you will sum up to 1. That is what your softmax is. That means softmax, what it does, it creates a probability so that the summation of the probability belongs to 1 for all of this output. Okay, so 1 3 4 2, it will create a probabilistic value for all these four, and when you do the summation of all these four probability of this four elements, basically you will sum up to 1, right? And that is the confirmation you will get from these two lines of code. And the final one is what your argmax is nothing but which index will provide you the highest number, right? Highest probability class with highest probability. So from this 1 3 4 and 2, we can see that this one has the highest probability, and according to Python, which follows the zeroth index leveling, right? So 0 1 2, so the second uh, input basically has the highest probability, right? So if we run this cell, we can see the same thing. So your input is 1 3 4 and 2, right, in form of tensor. Then your output, you can see this is the probability of each one of these. Okay, and this fourth number of value, that means the index 2 has the highest probability, and your argmax is simply returning the index of this one, right, which is 2. So I hope it is clear to everyone till now. Now next one, as you can see that we have already built the model, right? So to complete the model, we need to pass two things, as we have discussed in the previous tutorial. One is optimizer and one is loss function, and here we are passing matrix accuracy, or else the default is loss. Okay, so we are also passing accuracy in matrix, and as we have 10 categories, so we required this sparse categorical cross entropy for loss, and in optimizer we're using Adam optimizer. So we'll be also dealing some tutorials for this optimizers and loss functions, right? Which one to use in which use cases, right? And now your metrics here we are providing as accuracy. So model.compile will complete the model, and then dot fit will actually run the model and gives you the output. So let's just first compile and see the model. Okay, so as we already know, for that the code is model.summary will print out the actual structure and how many parameters. As you can see, it will approximately train 4 lakh parameters out of this. Only I think one hidden layer is there, right, of 128 units, right? Okay, so we have passed 128 of 5 to let me just quickly check, right? Yeah, dense 128, and your 28 cross 28 brings you a 784, right? So the total number of trainable parameter is approximately 4 lakhs. Okay, now if you run this model.fit, and within model.fit there is only one thing to understand, that is the number of epoch, and what you are going to pass basically your training data. So you can see this list contains here all the images, this list contains all the levels of those images, and this epoch is nothing but number of iterations you want your model to understand the data or undergo the training. So let's run it and quickly come back after the training is completed. So as you can see that our training is completed, all the 5 epochs completely, and our model has achieved a pretty good accuracy of 0.9, approximately 91%, and the loss is 0.25. Okay, so for loss we have used sparse categorical cross entropy. So you can also see what this loss function actually is in your home with when you have time, because all these are pretty much important, right? So if you see what is the function behind this, so you can see the actual source in GitHub and also understand what this code does, or how basically how this function works from here, right? Or if you just required a basic understanding, you can search on Google or anywhere, you will get all of this, right? So let me just close quickly all this because we are not going to deal all of this in this class. So yeah, once the training is done, we require next thing is model.evaluate, and in this evaluate function we are going to pass that another two list that we have. One is our testing image and one is our testing labels. If you pass and run model.evaluate, you will see the model is performing pretty well on the unseen data basically. So this one is the unseen data on which you have to do the inferential statistical test, and you can see okay, the accuracy here is approximately 88%, and the loss increases slightly, which is pretty much obvious. Okay, with only 5 epoch of training, right? So 35 is the loss, I think 0.35 is the loss, and 0.25 in the training. So it's pretty much okay, you can say, right? And now one more thing is dot predict function, right? What this predict function will do is this predict function will take individual images basically, and it will predict the value or the levels in terms of probability. Okay, and you can see this probabilities here. Okay, so your classifications will hold the prediction for all the test images. So if you see how you will understand, right, your test images dot shape, so you will see there are in total of 10,000 images. This is the number, and 28 cross 28 is nothing but width and height of the images, right? So same thing you can see in this classifications as well, right? So you do this, so you can see 10,010. So where this 10 is coming from, this 10 is nothing but your levels. Okay, so if you go in upside, you can see your data has 10 levels, right? So that 10 levels in form of probability you are getting in this classification object, and your classification object is nothing but the output of your predict method. So let's quickly revise here things that we have learned. So first thing is sequential that we required for creation of model. Then within that, for any image, we require this flatten. Then we require for hidden layers dense. Then in activation, you can do anything. There are many activation functions available, but we are implementing ReLU here. And in the final activation, as we are dealing with multi-class classification, we are applying softmax as the activation. And another thing is in your compile section, two things are majorly required. One is optimizer and one is loss. So we are using Adam optimizer for optimization, and loss we are using sparse categorical cross entropy. And then we are using this summary function for printing out the summary of the model to see how many parameters it needs to train for learning. Then fit method we are calling, and we are passing all the training objects so that it can train, and only one parameters that you can hyperparameters basically that you can tweak here is the epoch. And once that is done, your model is ready with the learning that it requires. Then you use evaluate or predict method based on the requirement. Okay, so that is the overall basic punchline or whatever the structure of your this deep learning thing. Right now the next thing will come, right? Okay, now the first, you remember we have implemented only 128 neurons in the model. So what will happen, let's say if we change the 128 neurons to 512, or let's say 1024, that one thing right now we can see, right? So we have kept everything as it is, and only instead of 128 we have increased the model hidden layer neuron to 512. And once this model is compiled, let's also print the summary so that you can see the number of parameters it needs to train. And let's just quickly come back once it is done, right? Okay. Uh, okay, somewhere it might have failed. So I guess something wrong with the API calls, nothing to worry about. So now if you do a model.fit, it will train the model. And again, right, if you see the evaluation where it is, yeah, if you do model.fit and then you do model.summary, it will print the summary. Okay, and here as you can see now, right now we have 512 neurons, right, in place. So this is the parameters. Okay, so this is the total number of parameters that it will train. Here same thing, but only thing that you can see here right, with increasing number of hidden layer neurons, your first epoch takes quite a good amount of time if you compare it with the previous one. So it consumes more time, right? It consumes more time in training, and for accuracy purpose, if you see, it does not reflect that much, right? Your loss function is 0.27, 0.28 basically, whether previously it was 0.25. Okay, so it does not deviate much. Now if you again do the same thing, and again let's say you increase the neurons to 1024, and then again do the same example, right? Then you do again the fit. So here you can see the difference more prominently, right? So by increasing the number of dense neurons, basically in your, I mean the number of neurons in your hidden layer, the training time increases significantly, right? Previously it was around 15 seconds for both the cases, but this time right now it increases to 26 seconds, right, for all the epochs you can see here, right? But the loss didn't come down, I mean it didn't came down significantly, right? So this concept in machine learning basically, or deep learning, whatever you say, it's called basically overfitting. So we'll be talking about all of this when we deal about this machine learning tutorials and practicals we'll be doing, right? And again, now if you do a model dot summary, you can see the change and the number of parameters it is training. So it is training more parameters compared to previous, but it is not significantly improving the loss, right, on the same training set. That set. Now the second thing what we are trying, so one thing you have to remember is the shape. So mostly people fails to implement neural network at the very early stage, is that they don't understand the shaping concept, right? So everything, let's say it's NLP project or it's a computer vision project, everything is nothing but numerical data, and you everything is basically tensor or vectors, right? Or you can imagine all of it as array of numbers. Okay, so this flatten, if you remove this one, then your whole project, or let's say your neural network, will not work, right? So let's try that one, right? Let's We have removed this one, and if we run this, so you can see this it provides you a shape error, right? So it is expecting a shape of 896, but it got a shape of 3232 and all, right? So you got this one, right? So first thing, you have to make sure that your input follows the exact shape you provided in the model, right? So your model needs to have accurate information about what is the data it is going to train upon. Okay, to a flatten, then definitely it will work, right? I'm not going to run this one because stop this one execution. Okay, now next thing, that to try out the same thing that we have tried for input portion, we'll be trying the same thing for output portion as well, right? So in output we have 10 labels, right? So that's why we are passing this 10 number, right, or the number of outputs. So let's say if we change it to 100, you will see it will fail again, right, in compilation, because as soon as at the time of training it will see values, it will fail. Okay, so for 100 it will not fail, but for, let's say, values less than 10, it will fail, right? So that one thing also we have to remember. And let's see, like with this dense of 100, what output you will see in classification and test level. That is another interesting thing that you have to watch out for. Okay, so now you see, you are seeing 100 levels here, right, in classification, and it is classifying, let's say, accurately, right? Classification level is accurate, but the number of logit here, the number of uh, nodes basically in output section is 100, which is not actual, right? So you have to be very much cautious while defining the input structure and output structure, right? So for output structure, we have 10 classes, we should restrict our neurons to 10, right? For I mean actual structuring of the network. So now let's say if we change it to lesser values from 10, let's see how it reacts. See now, any, because it has more values in the level section, right? More than 3 or 10 actually, 3 basically. So that's why while it is doing the training, it is throwing the error, right? So these things you have to be very cautious while doing neural network or implementing neural networks at the very beginning, right? So first thing is this input layer and the second thing is the output layer. So this shapes needs to be matched exactly based on the data, this thing. Now let's move on to the next thing, that is adding different layers, right? So till now whatever examples we are doing, we are performing all this task based on a single hidden layer, right? So you can also copy paste and increase the layers right here. So let's increase one layer here and let's increase another layer here, right? And let's make it let's say 128. Let's make it up again 128 for purpose so that it can close quickly, because if we increase the number of nodes, what will happen, the training time and overfitting and all that we have checked, and now we are only trying to see if we add more layer whether the performance increases or not, right? So let's just quickly run this, come back once it is closed, right? Again, you can see here that in the final layer we have implemented ReLU as well as a dense of 128 instead of softmax and 10, right? So that's why you can see this deviation in output, and you can see how your loss function is not making any sense. But well, definitely with this index it is accurately classifying uh, the thing or whatever the image as angle bot. So let's just quickly change it to soft max. Okay, and this one is just 10 as it will be your dense layer, and we have two additional layers. So instead of one layer we are having now two hidden layer, right? So you can try this portion also in home and see what difference you are getting. Now next hyperparameter that you can tune is epoch. So I'm leaving it for you for your home training or something like that, and you can try and comment below like what difference you see compared to this epoch is 15 versus, okay, let me type 15 versus 5, right? And you can comment it below this video. Okay, now next one is your this thing. First one is your normalization of images, right? So what will happen if you don't normalize and you pass the array as it is? So let's just comment out this two line now in this section for understanding, and let's pass, run this model as it is. So you will see a huge amount of increase in time. Okay, so that is the first thing you will see, and also the deviation in loss that you can also see. So for accuracy, you have to include the metrics part as well that we haven't included for long. So in the very first model, if you see, we have included accuracy as part of metrics, right? Yeah. So we'll just copy from this one and we'll paste from the next code block onwards, right? So here, but you can see, yeah, how your model is performing if you use this normalization versus if you don't use this normalization method. So with larger data, actually your image data are very large and not a kind of a grayscale thing, right? So in that case you can see the difference, but here, yeah, is not performing that bad. Okay, so within 16 seconds, yeah, your training is getting completed and you are also getting good loss here. Okay, now, so a quick recap what so far we have learned. So if you see from here, right, after understanding how to structure a keras sequential layer, we have learned all the different hyperparameters available, from activation to flatten, sequential, then dense, then what is softmax, and how to set the input output and all that. So I hope right now if any machine learning problem you will have and you have the basic understanding of your input shape and output shape of the arrays, then you can definitely implement a neural network from scratch using Keras API and TensorFlow as a backend. Okay, now let's move on to the thing which is callback. So what is callback basically? So if you see, let's say for a machine learning trainer, right, the loss they have already defined. Okay, let's say I don't want a loss which is I mean, let's say for me, if the loss is below zero point 0.5, or let's say the loss is below 0.6, I'm okay. I don't want to train the network much further, right? Because for any deep learning projects, when you will be working with terabytes of data, this training will take days and days, like with this GPT, chat GPT and all, right? So the training takes very long hours. So for your internal projects, let's say you have defined that with the management that your loss, if it is less than below some threshold value, you are pretty much okay with that kind of a training. So what you can do, you can define functions like callback. What it will do at the end of the epoch, it will send all the accuracy, all the metrics, that means loss, accuracy and all, to the system. And if it is lesser than or greater than your defined threshold, then it will stop immediately the loop. It will store the model and it will send back. It will basically terminate the learning for that model, because the model has achieved the desired threshold output for that metrics basically. So right now if you see, we have defined one class for, and we have called it my callback basically. So what this class contains, this class is containing basically a module from Keras callbacks, and I mean from Keras callback module. So you can see the source here and how to implement the callback or the whole code. So we'll be going through this function basically. So within this callback class, we are defining one function called on epoch end. So what this epoch end requires, the number of epoch and the logs, right? So this logs will collect the logs, that means your loss, okay, and or accuracy, whatever, right? So right now the logic we have set, if my log contains an accuracy which has more than let's say 60%, right, then we have reached 60% accuracy, we are okay with the training, and we'll immediately terminate the training, right, and free up the memory or RAM, whatever, right? And then we are just calling this class here and storing this object. So once the object is initiated, we can use the object to call this function, right? That is the basic of your object oriented programming. So same thing we are doing, and where we are calling all of this, we are calling all of this in the fit method. So fit method has the option of callbacks. So if you hover over here, you can see, right, when in tab, if you click, so you can see your fit method gives a option additional parameter basically for callbacks, which is by default none, but you can see the definition how you can implement. And even if you don't create this class and all, right, you can directly use this tensorflow.keras.callbacks.callback from here. You can use the method to implement the same feature, right? It's much more what easier if you just create a class like this and then call, and then you can tweak here, and based on whatever you're tweaking, your model will perform. So the same thing you can see here, and if you require much more details, you can see here, right, in the callbacks. Just quickly close this one, and then again this fashion MNIST data, right, whatever we have done so far, again we are loading here, and then same, your callback class is getting created here, and it's much more structured, right, the definition. Okay, so what this function is doing, it is currently it is saying, so previous function, as you can see, we use the accuracy matrix, and we mentioned that okay, my if my accuracy is more than 60%, let's halt the training. And in here what we are doing, we are using the loss, and we are telling, okay, if my loss is getting lesser than 0.4, then we have achieved the threshold or whatever we are testing for, let's close it. Okay, same thing with the different logs, because your logs will contain accuracy and loss, both the matrices, right? So once that callback is initiated, then you can use same fit method, and in fit method within your callbacks parameter you can pass the callback, and here we have run it right by providing a pause to 10. You can see after the third iteration, basically after the second iteration, basically when your loss reaches less than 0.4, it is canceling the training. So the third training is after this training, basically it is not happening any, so the model is getting stored, and then you can simply use this model for your testing purpose, because what you wanted from the model, it has already learned, right? So a quick recap for this session, what you have learned, basically you have learned the basics of computer vision and TensorFlow neural network implementation for any vision approach. So how to structure or how to formulate a neural network for any vision problem. Then you have gone through all the hyperparameters required to structure the neural network, and then finally the callback or implementation of callback, right? So that's it for this tutorial, for the second tutorial. In the third tutorial will be dealt and will be looking forward to teach or explain much more details about neural networks and TensorFlow, so that you can easily understand all the functions behind the Keras API, and you can easily implement, and it will ease your machine learning and data science journey. Thank you very much.